Hi guys, in this video we're going to go over what is escape velocity and how do we derive the two equations so we can use them in different examples. Okay, so escape velocity, what is it? So escape velocity is exactly what it says. It's the speed that something needs to completely escape the gravitational pull of an object. So for example, if we have the Earth and I have a rocket on the top of the Earth and I want that rocket to go out into outer space, I want to completely escape the gravitational pull of the Earth. We didn't know how much energy that rocket needs to completely escape that, again, that pull of the Earth. Okay? So if we look at our equations, what we can see here is change in work, change in energy is equal to mass times the change in potential. So just to recap, what change in potential is the work done per unit mass to bring a point from infinity, so let's say it's my 1 kilogram mass at infinity. So to bring a point from infinity to a point within that field. Okay, so for gravitational fields, we know that if I had a 1 kilogram mass, there's going to be a force of attraction pulling it towards the Earth. So because there's a force of attraction pulling towards the Earth, I don't have to put any work into the system to move it there. Energy is going to get released. So that's why when you look at the gravitational potential lines around the Earth, they're always negative. So we look here, gravitational potential is equal to negative gm over r. Negative g, the universal gravitational constant, times the mass of the body, Earth, divided by the distance between our rocket and the center of the Earth. So for this example, it would be the radius of the Earth. So again, another way to think about it then is if I had a rocket here, I would need to put energy in to completely remove it from the gravitational pull of the Earth. So that's why, because I have to put energy into the system to remove it, that's why it goes from negative energies to zero energy. So we're saying zero potential is at infinity. So again, what we're saying is, we want to put enough energy in. So if this rocket is moving, if it's escaping, we know it's going to have kinetic energy, and kinetic energy is 1/2 times its mass times its velocity squared. Or you might see it written as EK is 1/2 of its mass times by its velocity squared. So if I want to define escape velocity, I know that its kinetic energy, which is 1/2 of its mass times the velocity squared, must be greater than, to completely escape the pull of the Earth, completely greater than that gravitational pull from the Earth, that energy to completely remove it from the field. So the energy I need to completely remove from the field is going to be its mass times by its change in potential. And because we're going to go from a potential line to zero, the change is just always going to be whatever the potential was to begin with, right? Because the change in potential will reference it to zero. Anything minus zero adds zero is just the number we originally started with. So again, we want it to be greater than this. Okay, so one way we can do it is we can say that the potential was equal to our negative gm over r. Okay, so potential tells about the direction, right? It tells it's a negative number here. But energies are scalars, so we don't care about the negative. So that's why we can say that our 1/2, we're looking at the magnitude, 1/2 mv squared must be greater than the mass times the potential gm over r. This is the little m. This little m is our kinetic energy of our satellite or of our rocket that we're trying to launch. So that's why our little m's will cancel. And what we get left with is the large m, which is the mass of the Earth or the body we're trying to escape from. So what we're going to say now is to find out how much energy we need to escape, we're going to look at the extreme. We're going to look at what is, when they're equal, what is that minimum speed it needs to escape. Because we know then we're going to need a speed greater than that number. So what you can see now is that V minimum squared is going to equal gm over r times by 2. So V minimum is going to be equal to the square root of 2gm over r. So I want to find out the escape velocity for any body is on the center of the Earth or on Earth. We do 2 times the universal gravitational constant times the mass of the Earth divided by the radius of the Earth. We can do it for any object. Let's say that we've got an object on Mars, and I want my object to escape the pull of Mars. Its escape velocity is 2 times the universal gravitational constant times the mass of Mars times the distance between that object and the center of Mars. It'll be the radius of the Mars. You can do it for the moon. You can do it for any object. The other way we can look at it then, the other equation you might see, is the other way that we can write potential. So we just said that the kinetic energy must be greater than the energy, the pull of that energy because of the gravitational force of attraction. So the other way we can model it is that 1/2 of mv squared must be greater than the mass times the potential. And again, we can write potential as g times change in r, the change in position. But again, because the change of potential is we're going out to infinity, we can say that it's just the potential, and we don't need the negative because, again, energies are scalar. So we just write G times R. So what we can say now is that we can see that we cancel our two little m's, and we can see that V minimum, or escape velocity, must be equal to, because again, if we calculate the minimum, we're saying what point are the equals. We know any speed greater than that number. So V minimum is equal to the square root of 2 times GR. So we'd use this one if we know the mass of the Earth, say, or the mass of the Mars. And we'd use this one if instead of given the mass, you were given G. So like, for example, G on Earth is 9.81. So if you found the video useful, just remember to click the link below to get signed up to our lessons.